that we talked about earlier. So these are all of the kinds of sessions we attended. Some of these sessions were very high-end facilities where we were standing there just with the surgeon and the patient. In some of the other facilities, we were actually in such a scenario where there was a very large amount of patients and their caretakers all surrounding the doctors, and complete chaos in terms of the levels of noise, and so we were able to get a much clearer understanding of the problems, having seen it from all directions and all domains. Next, once we found out what the actual problem that we wanted to solve was, the next stage was finding the solution to it. So the first step in finding the solution was the ideation part of it, where we tried to break down the problem into multiple small problems, and then we started to find out which part of the solution will address each of the part of the problem, and then we integrated it all. Once how the solution would work was slightly clear to us, the first step was to generate a proof of concept. The proof of concept in the journey of a product is the first stage where you do not want a product, you do not want users to use it. You have a scientific principle in your mind and you want to validate that that scientific principle works. What we wanted to replicate with this proof of concept was that we are able to provide the suction pressure at the level that we are setting. There is no variation in the level of pressure that we provide. And second, we are able to provide oxygen at the required flow rate. There is no variation in the flow rate of the oxygen that we are able to provide. Once we developed the basic proof of concept and we validated these parts, we then moved on to the prototype part of it, where we wanted to make a product that was ready for the field, that we could take to the doctors, that we could take to the patients, that we could get an understanding on how the patients or the doctors or the nurses would interact with that. So in this part, if you see, we made foam and thermocol prototypes, which would give a rough estimation on the size of the device. We printed several screens, which would give the kind of interaction that the device would have with the users. So each of the user interaction screens was printed, and we showed those screens to the users one by one in order to understand if the users are able to understand the flow of the using of the device. We then started to calibrate the software so that we could get accurate readings from the sensors, and we could then make our control systems that could function the pumps and the oxygen supply units accordingly to have optimal delivery of all of the therapies. After that, we made the CAD designs and then 3D printed the first enclosures of the device so that we could compile everything into a single body and then actually take it to the user to get the first-hand experience and first-hand interaction of actually using the device. With all of that information and all of the data and user feedback gathered, we then moved on to the second stage, which was the prototyping stage. So earlier in the proof of concept stage, all that we did was we made a system in which only the basic fundamental modules of the therapy were working. But when we come to the prototyping part of it, these prototypes have to be ready for bench test. These prototypes have to be ready for use on the field. This means that these prototypes would also be used with the patients, and the doctors would be using these prototypes. So in order to make sure that these prototypes are worth actually using with the patients, these were the kind of steps and processes that we went through. So once the basic concepts are validated, the next stage of going to the prototype is forming and refining a system architecture. So the system architecture is basically a top-down approach. It is an eagle's eye view, looking from much higher, much far away. You are able to understand that what would be the basic units of the system and how a very crude understanding of how those units would interact with each other. For example, if we talk about a camera, so going to the eagle side view, the basic elements of the camera would be a sensor, a battery or a power source, a button, actuation button, a lens system. So all of these four are the major components that would interact with each other in order to make a camera that the user can use. Once you have this system architecture laid out, you can then go into the details of the hardware and the software aspects of it as to what would be the requirement as per the user requirements, what would be the hardware requirements, what would be the software requirements. So the system architecture helps you understand that side of the problem. So for example, once you have identified that your camera has a sensor and it has a lens, you can then go into the details of what would be the size of the sensor, what would be the resolution of the sensor, what kind of sensor will it be? Does it need to does it need to take colored images? Does it need to take monochromatic black and white images? Or does it need to take low light infrared images? So that part of the further details of the component requirements comes once you basically know what the components are and how they would be interacting. During this process itself, once you have the system architecture, you also go through the process of risk management. So each of the components in your camera may fail, and that might stop the functionality of the product, and that functionality of the product might cause a major problem or a major issue. So for example, if you are a hobby photographer and you are going to a vacation with your camera, the worst that can happen is your camera will not function, you will not be able to take good images, but still you will be able to enjoy the vacation. But if your camera is installed on a self-driving car and then your camera system fails, your car will not be able to look at the obstacles, your car will not be able to navigate in the city traffic, and then there are two possible outcomes. It will either crash or it will not run at all. Both of these are very undesirable outcomes, much more severe than actually having a vacation without pictures. So those kind of risk understanding and assessment is very important so that you have your backups in place. After that, the next step is to get the user feedback. So if you made a very good product that the user does not want to use, then that product is not going to change anything in the lives of anyone. For example, Linux is a very good software, a very good operating system that many hardcore users use very effectively. But for the mass population, it is not usable enough. It is not easy enough to use. On the other hand, Mac OS and Windows are so easy to use that they enjoy a much larger user adoption than Linux. So that is where user feedback becomes very important. Further, when we talk about hardware systems, the user interaction and the user feedback early on is very important because each iteration of the change of hardware requires a very large amount of cost. So there might be a product that you are able to manufacture for 10,000 rupees, but the first batch of PCBs that you will manufacture for that product would be costing upwards of 1 to 2 lakh rupees, because for a small batch, for a very early batch, there are all of the processes that are to be set up. So you cannot keep on changing the design and again. So as soon as you get the user feedback, if you get it very early on, there are less things to be changed further down the line. There is less investment required in changing those things, and less time and cost would be required to get a very good product that the user is happy to use. After that, this becomes a lot more important in any of the regulated industries. So when we talk about automotives, when we talk about medical and healthcare, when we talk about space technologies, it becomes very important that the products do not fail. It becomes a lot more important that the product should not cause a harm. Even if the product is not able to achieve its intended outcome, if it is not able to give a benefit, that might still be considered as an okay outcome, but it should not be causing any harm to the user or the patient or anyone around the user. So for those things, the governments usually have the regulatory restrictions in place considering the kind of severity of the harm that might be caused to the user. So you have to keep in mind that once you're developing the product, after you have developed the product, you will have to go for regulatory certifications. You will have to go for regulatory permissions until the proper certifying bodies provide you with those certifications or allow you to make that product. You cannot create, fabricate, and sell your product even if your product is excellent. You need to prove that this product is excellent. And a part of this comes from the design aspect of it, where you're recording every stage of the design. You're recording the first idea that you have. You're recording what are the flaws in those ideas. You're recording what are the good aspects of those ideas. Then you work on the second iteration of that idea. and then again you do the same things, that what things you improved from the previous stage, what things became slightly less improved from the previous stage, what additions you're doing to the product, and why you're doing that product. You need to know the components of your product. Why have you chosen that? Do they justify the use case scenario? If you need to take a high resolution picture of the space, you cannot use a 1.3 megapixel camera from 20 years ago or 10 years ago. If you want to make a CCTV camera that can operate on low light, you cannot take a very high resolution camera that only works on daylight. So each and every aspect of the choice of components, the interaction of the components, the choice of circuitry, the processes that you are deciding to fabricate that product, each of those things have to be kept in mind. So for example, when we talk about medical products, one of the crucial aspects for things that touch open wounds or go inside the body is biocompatibility. So any product that we are using for anything that goes inside the skin, goes inside the body of the human, it should not cause any kind of allergic reaction. It should not cause any kind of cancerous growth. It should not cause any kind of harm to the body. So it has to be made from a material that is compatible with the human body. Those materials are called biocompatible materials. So while designing the product, you have to ensure that whatever design you are making, if it is going to interact with an open wound, if it is going to go inside the body, then it has to be made from materials that can interact with the human body. This means that some of the processes will have to be changed, because if you're using titanium to make a part, you cannot follow the same processes for manufacturing that you will use for maybe making the part from aluminum. The cost of the manufacturing processes will change. The processes actually themselves will change. So those considerations also have to be taken care of this time only. And so I've already covered a part of the safety considerations as well. But these safety considerations go on to the electrical safety, the biocompatibility, as well as the usability safety part of it as well. So for example, there are several cases where we are trying to shut something close, and then maybe one of the fingers gets caught inside and it pinches us or hurts us. So you have to keep in mind the kind of scenario where the product could be used. If it is going to be used in a high stress environment where the user will not have a lot of time or attention to pay to the product itself, then you have to make sure that the product is safe enough so that you do not have to divert your attention away from the actual usability or the actual task that you're using. So for example, many of the entertainment systems and air condition controls in the modern car come with touch sensors now, capacitive touch sensors now. So in my opinion, and I believe Pradeep sir would be the best one to guide on this, I do not believe that these are good systems to deploy on a car, because when you do not get any tactile feedback when you are using a smooth touchscreen or a capacitive touchscreen, you have to take your attention away from the road and you have to look at the touchscreen to be able to change the temperature of your ACs. But in good cars, which in my opinion are good cars, they still have those tactile controls. They still have those dials. Even if you are not looking at the dial itself, have your entire attention on the road itself and the traffic, you can still reach out and you can feel that dial and you can understand the tactile moving of that dial. So all of this lead to the actual safety considerations and the safety during usability of the product itself. Apart from that, there are electrical safety considerations. So all of our laptops, phones, chargers, if you see, come with an ISO 10950 rating that is written on all of your laptop, phones, and chargers. This is a normal electrical equipment safety standard. This means that while you're using the laptop, you will not get electrocuted. You will not get any kind of electrical shock. Or even if you feel some kind of electrical shock, it won't be very high intensity that it leads to you getting any kind of injury due to that electrical shock. So those kind of safety considerations have to be made inside the product while designing it itself, because if you have made the entire product, which is like a window or desert cooler that we used like some years ago, so the local coolers would generally, the people would advise you do not touch it bare hand, you do not touch it without wearing slippers. This was because there was no consideration to electrical safety. Your local mechanic would assemble it using local no brand components, and anyone touching it might get electrocuted. So all of those safety conditions have to be kept in mind in the initial phase of the design of the project itself, so that you do not have to make any major changes once the product is ready. And in order to make sure that all of the other aspects of the product design have been taken care of in the prototype, we undergo bench testing, and then we undergo certification from an external third party authorized body. So in the bench testing itself, we test the product for each of the parameters. We need to understand which parameters of the product that we need to test. We need to understand how long are we going to test those parameters. We need to understand the accuracy, that what is the accuracy of the data that we need to gather to make sure that the product is working well. And we also need to consider the acquisition rate. So for example, if any of the parameters of the product are changing very rapidly, then you need sensors that have very high data acquisition rate, so that they're able to identify any small variations or any short duration variations also in the during the operations of the device. Now, so this, for example, is the system architecture of our product InnoHeal. So we have a centralized controller. This centralized controller works with user inputs. It sets alarm buzzers or alarm tones. It interacts with the LCD graphics display. Then we have a completely different power management system that interacts with the charger, that interacts with the battery, and that makes sure that once you remove the charger, the device flawlessly, seamlessly switches onto the battery, so that the device does not switch off when you are putting the charger on or taking the charger away. Then we have the other parts of the actuation system that all interact with the microcontroller. Having this system architecture in place helps us understand that what parts interact with what other parts, and it also helps us identify what would be the interactions between these parts. The next part of it was the risk assessment part. So the risk management has basically two sections to it. First is the risk assessment part. Whenever we are looking at a risk, we need to identify that in the entire system, looking at the system architecture itself, what can go wrong? What are the components that can fail? What would be the impact of that failure? Is it going to be like, even if that component fails, there is not going to be any major harm? Or is it going to make the entire system useless? For example, your PCs or your laptops may have 3 to 4 USB ports. If one of those ports fail, you still have 2 or 3 other functional ports that you can use. So the failure of that one port is not a major problem. On the other hand, your devices usually have only one keyboard. So if that keyboard fails, then you have lost entire access to the system unless you get a different keyboard. So one part of it is what can go wrong. The other part of it is, if this thing goes wrong, what kind of harm it will cause. The next part to assess is, what is the probability of that failure. So if that component is coming from a very good manufacturer, for example Bosch or NXP or ST Microelectronics, so these are very reputed industries in their own fields. If you buy components from them, there is a very less chance that those components will actually fail. But if you are using a component from a local vendor or a local supplier, there are chances that that component may fail unless that supplier itself gives a lot of attention and a lot of attention to detail while manufacturing of all of those components. So you need to understand what is the probability of that failure. Any component that may fail very easily might need production to be built around it. So for example, you might be using a sensor that is very sensitive to the amount of voltage that it is receiving. So any variation in that voltage might blow up that sensor. So if you are designing a circuit around that sensor, you need to make sure that you have a zener diode in place or any other kind of voltage protection mechanisms in place, so that any spike in voltages, any variations in voltages gets bypassed before they actually reach that sensor. So the sensor never blows up. So this is like many of our laptops and our even our spike guards that we use with our computers, they have a fuse built into it. Many of the modern ones come with a electronic resettable fuse. So any sudden variations in voltages blows up that fuse, and due to that, those spikes in voltages do not reach your electrical equipment, and that fuse is easy to replace. It's only a 5 rupee component that can replace easily, and the device is functional again. So those kinds of protection mechanisms are built in because the users were able to assess that voltage spikes might come through the wall outlet, and those spikes might be damaging the laptops or computers or any other electrical equipment that they're using. So once you have identified the probability of failure and the severity of the harm, you then identify how critical is it to mitigate that risk. So for example, if there is a component that has very low chance of failure, so maybe if you're buying a sensor from a very good manufacturer, and maybe out of 1 million of those sensors, one might fail. So there is a very strong likelihood that in your entire product life cycle, there might not even be a single failure. So you do not need to make any kind of, you do not have to make any kind of considerations or safety mechanisms in the place. But if there is a very large amount of failure rate or high probability that something might occur, so for example, on laptop, in a laptop or a phone, there is a high amount of probability that the user might drop the phone, might drop the laptop. So for any of such equipment, you need to make sure that you have considerations in place that this event is most likely going to occur. So you have to mitigate that risk by combining the probability of failure and the severity of harm that failure might cause. You are able to identify the criticality or the severity of the risk. Any risk that has very large rate of failure and very high severity of failure has to be solved at any cost. You cannot make the product without solving for that risk. But if the rate of failure is also very low, the probability of failure is also very low, and the severity of harm that failure may cause is also very low, then you might take a conscious call on whether you want to solve that risk or not. So once you have done the risk assessment cycle, you then go to the risk mitigation steps. The risk mitigation steps might involve changing the design of your product so that you have the risk mitigation design into the product itself. So maybe if you are making a product that takes direct voltage from the wall outlet, and you do not want to risk the electrocution of anyone using that device, you might choose that you will not make the device from metallic components. You will make the entire enclosure of the device from plastic components, which would be an insulator and which will protect your user. The other part of it would be component change. So maybe instead of using a power supply that is coming directly from the outlet, you might be using a charger that is similar to the modern day chargers, where the direct power coming from the wall outlet gets converted into DC outlet in the charger body itself, and then the kind of voltages that are actually coming out to the laptop or the device that you will actually be touching are low enough so that they do not cause any severe harm to you. Another way of mitigating these risks might be if you know any of the barrel connectors, like the old Nokia chargers that we used to have, or even the barrel connectors of the chargers of the laptop that we have. All of these barrel connectors have ground on the outer terminal of it, and the voltage source, either 12 volt or 18 volt, is on the internal terminal of it. So having the outer shell ground means that even if you're touching the entire system, even if you're touching the tip of the charger, there is no probability of you actually interacting with the component that is actually carrying the charge. You are touching the ground or the earth component that actually takes away the current back to the ground, and that is a layer of safety that is built into by design and the design of the components itself. Apart from that, you also have to take care of the factor of safety. So if there is a probability that instead of having 12 volts throughout your entire system, there is a probability that the voltage may go up to 15 volts. You take factor of safety into account and you choose components that are good to work even up to 20 volts. So this means that even if you are not getting 12 volts continuous, even if there is a spike up to 15 volts, it is well within the actual operational voltages of the components that you are using. After that, you might also choose any backup component for fail-safe. So for example, instead of using one sensor, you might choose two sensors. There are several devices that now come with two batteries, which is partly because of the ease of usage of the product, and also if one battery fails, the other battery is still powering the entire system. The last stage, if the risk is so great that you are not able to mitigate it completely, the technical challenges are too difficult, and you still want to launch the product, you still have to launch the product because there is no other solution available, then the last stage comes, that is the user training for safety, in which you generate a very thorough user instructions so that anyone who is reading those instructions can understand how to safely operate that product, how to safely use that product. You try to understand, you try to conduct training sessions. So, for example, when the lathe machines or any of the CNC machines are installed within the campus, a representative from the manufacturing company visits the campus. They train the students, they train the operators of the machine, and they even train the faculty in charges so that everyone knows how to safely operate the machine, how to identify the reasons, the causes or signs of failure, and how to make sure that any maintenance and any protective action is taken well before any of the failures actually occur. So that is the last stage where you can actually assess, you can actually help mitigate those risks. If your users are capable, if your users are trained, then those risks are mitigated by themselves. So once this risk mitigation exercise is completed, you have your refined design of the product ready. You do not go into production. You go back to the risk assessment again. You follow the entire process again, and then you see if all of your risks have been removed or brought down to a level where they are acceptable for actual field use. Once you have ascertained that there is no further risk mitigation required, everything is solved and no further risks remain with the product, that is when you go to the next stage, that is the actual fabrication of the prototypes and the bench testing of the prototypes. So for bench testing of the prototypes, you have to identify all of the protocols, all of the parameters that you want to monitor, the accuracy with which you want to monitor the parameters. Then you identify all of the available sensors, all of the available meters that you can purchase off of the market, and you can use them to assess how well your product is working. In some of the cases, you might need to make your own testing setup. So, for example, we were able to get a manometer that measures the pressure within the wound area. We were able to get a flow meter that was able to measure the flow rate of oxygen that we are supplying to the wound. But we could not use all of these sensors with the patient directly. So we made our own wound bed. This is a model wound bed. It works very similar on to how actual wound might be there. We made provisions for supplying of exudate, that is the liquid that the wounds might be oozing out. We made provisions for supplying that liquid through to this wound bed so that the actual working of the machine can be replicated. We also made provisions for several outlets so that the position of these manometers can be changed and we could monitor that the actual pressure is achieved throughout the wound volume, not just one corner of the wound or one small area of the wound. So you need to design your own, you may need to design your own testing setup itself to validate your product. So with this entire test setup, you then need to identify what is the rate at which you will receive the data. You need to identify how much data you will gather and what should be the duration of the tests. For example, our product is frequently used for sessions up to 72 hours, that is up to 3 days. So we did several tests of the product working with the entire wound bed for 72 hours to 96 hours. Once we were satisfied that our product works very well throughout the duration of 72 hours. So as you can see, the orange line over here represents the set pressure, that is the desired pressure that we wanted the device to operate on. And the blue line on the top is the actual MPWT pressure that our device was able to create onto the sample wound bed. These pressures are almost identical. There is negligible amount of variations between these two pressures, and there is no variation throughout the entire duration of the cycle. That is, throughout the 3 days, there is no variation. There is no difference in the pressure that we wanted to provide and the device was actually able to provide. So this gives us the confidence that our device is now ready to provide this kind of pressure to the patient because there are no variations, there are no failures. On the other side of it, on the flow rate,
you tried it on different temperatures also.
Yes, ma'am.
Like from north to south, we have temperature.
Yes, ma'am. We actually created those environments within our office itself, and actually one of the problems did come out during this entire cycle itself. So in the very early parts of the design, we chose some components that was temperature sensitive. So once we calibrated the entire system, we were able to achieve the accurate flow rates in the month of September and August and September. But once we reach the months of December and January in Delhi, the flow rate started to drift apart. So it would give the correct flow rate during the morning cycles when we were there, but recording the entire flow rate during the night. Once we came back, we saw that during the midnight that flow rates would change slightly. So then we identified that these components are temperature dependent. Then we bought a completely different set of sensors. We made we made changes to our system architecture as well. How the oxygen was delivered, that part was completely changed. And then we were able to achieve the required flow rates throughout the temperature ranges, throughout the humidity ranges, in all geographical locations.
About me, you must have set some upper temperature limits and
Yes, ma'am.
humidity
So
limits.
for that, once we are designing the system architecture, we need to take into account on what exactly are the user settings where the product will be used. So if it is going to be used in outside environment, it might be used in Kashmir, it might be used in Tamil Nadu, it might be used in the Sahara Desert. So we need to take into account that those devices have to work from all the way from minus 20 degrees centigrade, maybe up to 50 degrees centigrade. We also have to take into account that the actual working temperatures and the storage and transportation temperatures may be different. So, for example, something that is being transported in a container in a ship near around the equator, the temperatures inside the metal container might go upwards of 60 or 70 degrees, even though in the actual usage scenario that the temperatures would be around 40 or 45 degrees. So we need to make sure that if the product is stored at very high temperatures and then used at normal temperatures, then also it is not failing. So all of those considerations come into part during the system architecture and then the product development part. So by testing the flow rate, we noticed that the initial flow rate of oxygen was high for a very short duration, but after that, for the next 72 hours again, the flow rate of oxygen was maintained to the desired value. So this again gave us a confidence that initially, since the wound has no oxygen, it is already deprived in oxygen. Even if the oxygen supply rate is slightly higher, then it is still within the safe limits. And since after that, the entire during the entire duration of the testing, there was no variations in pressure or the oxygen supply. We were sure that the product is now ready to go out for further testing. Now, even at this stage, we were sure that the product works. We wanted to make sure that no one questions our methods of testing. So what we did was we went to DeW, which is a globally renowned testing agency, and we sent our device for electrical safety testing. So they tested our device, they tested the functionality of the device, they tested our device at different temperatures, at different pressures, at different electrical levels. So during the testing itself, they created electromagnetic fields around the device to make sure that the device does not malfunction or misfunction. They created various kinds of electrical disturbances. They removed the electrical supply for a small duration of time. They gave sudden very high voltages for a small durations of time. And all those kinds of things that might actually be undergoing, that the device might need to undergo while it is being used at home on the patients, while it is being used at hospitals on the patients. All of those kinds of electrical and electromagnetic disturbances were provided to the device, and the device did not malfunction on any of those conditions. So with this, they were able to certify that the device is ready for actual use in the Indian electrical settings or the Indian settings. So with this, with all of these test data, that is from the electrical safety test data, from the permissions with the CDHO, with the bench test data that shows that our device functions flawlessly throughout the therapy durations, we approached AIMS New Delhi, where our mentor decided that now, with all of that data in mind, it was the device was ready to be used on patients and see if it is benefiting the patients or not. But before it could actually be applied on the patients, we needed to take permissions from the ethics committee of AIMS New Delhi. So this ethics committee comprises of senior doctors and researchers who look at all of the data that we submitted, who look at the potential harm that could be happening to the patient in case the device fails, who look at all of the benefits that the patients will gain if the device works properly, and then they decide if the device can be used on the patients or not. with the kind of data that we have generated and with the kind of permissions and the certifications that we have received from the external bodies before we approached AIDS, we were blessed with the opportunity to actually see the device being used on the patients. So our mentors then started to like her team started to take patients in, and any of the patients who had any kind of severe wounds that would otherwise take very long duration or very long time to heal, those patients were set up on our device, where our dressing was provided to those patients, and the device provided the therapy in terms of the negative pressure or oxygen. So this is a CTRI registered AIDS study in which there are different. So this is one of the case studies where the patient actually had an amputation. So the entire leg was amputated near the hip joint, and early on there was some infections that was seen on the wound. During the entire journey, the wound edges came closer. The entire wound volume, as you can see in the bottom three images, which shows how the wound is progressing. Uh, the wound cavity got filled. If you can see, there's very slight whitish creamish stuff over here. This got removed so that the entire tissue became red. That is a good healthy tissue that is ready to close. And the wound came to a stage where a skin graft from the other part of the body could be provided onto the patient, and the wound was actually closed. Similar kinds of results were achieved for other patients as well who had traumatic road accident injuries, road traffic injuries, bed sores, diabetic foot ulcers, and several other wound care diseases. So, with our clinical studies, with our testing data, with our CDSCO permissions, everything in place, we are now finally available in market where the doctors from AIDS, from Gangaram, from Sir Gangaram Institute in New Delhi, and several other hospitals are now actually using our devices on the patients, and the patients are getting healed faster with lesser problems and lesser troubles to them. So this is what I had to share right now. If you have any questions, I welcome them right now.
Collecting data,
Uh,
how many patients and what severity of the patients, all the
Ma'am,
data.
all of that side is maintained by AIMS because they were conducting the trials. We were supporting them with the devices that we fabricated and the dressings that we brought. And for this first study that we did, about 26 patients were enrolled and multiple sessions were deployed to some of the patients. So the number of sessions that will be deployed to the patient depends on the kind of wounds they have, the kind of number of days of hospital stay that they require. All of that judgment is taken by the clinician. So there were some patients on whom only one session was required. There were some patients who required 2 to 3 sessions over a period of 1 month. Then we did another study that got the results of which were published during the AIMS Research Day. On that study, over 100 patients had been treated during the entire duration of that study using our devices.
Any more questions? Okay. Thank you.
So you have mentioned that some people will suffer from lifelong wound. Will this help for them?
Yes, our mission is to make sure that that statement stands for from this day forward. So our vision and our mission is to bring our technology and our devices to the entire population everywhere in the world, so that all of the wounds get healed and all of the patients get healed.
Right now, that position. Right now, does it execute that position?
Right now, since we've only been 1 year, less than 1 year in the market, it is probably early for us to say this. But with the results that we are seeing, with the kind of clinician validation that we are seeing, so during this period, we have spoke to a lot of doctors who have used our products. Many of the doctors who were skeptics, who did not. So what happens is, in many of the cases, even in India, the doctors do not believe that an Indian product can work as well as a global product. So they were hesitant in using our product. We offered our product to them. we asked them that please use this. We had data backing us up from the clinical study at AIDS. With all of that considered, they actually used it on the patients, and since then they have been continuous users of our product because they could see that benefit getting translated onto the patient and their wounds getting better. So, like I understand that it is still very early for me to say that we are going to achieve that milestone, but so far we are happy to see that we are on the right track. So, before I leave the podium,
Have you decided any life? I mean, is there any life of this equipment or
so
need upgrades?
on the consumable part, since they interact directly with the wound exudate and the wound surface of it, they have to be changed after every session. So, for example, instead of having 4 to 5 dressing changes in one day, one dressing and canister system deployed is okay for 3 to 4 days. So after 3 to 4 days, that dressing is removed and thrown away, and the device is good for 3 to 5 years, depending on the amount of maintenance that is provided to it after 3 years. So the service life of the device is good for up to 5 years. Yes.
That thrown away part has to be disposed of very carefully.
Yes, ma'am. That is as per the medical waste discarding guidelines. So that is why we recommend that the device be used and operated under the supervision or recommendation of a clinician only, so that they are able to guide regarding the discard of the medical waste, as well as they are able to assess exactly if the device is useful in that kind of wound or not. So before I leave, as a startup, we always have more ideas than the number of hands and heads we have. So if any of you wants to understand how a medical device gets built, we have projects that you guys would enjoy working on. You can write to us with your interest and with the projects that you have already conducted or doing on at our email ID contact@inochihealthcare.com, and I would be happy to meet you guys even after the session.
One more question.
Yes, ma'am.
What was the reason you used a Japanese term?
So, early on, when we were trying to look for a name for the company, we needed a name that was very easy to say, that would be recognized at multiple places, at multiple geographies, because we always knew that this product would be used not just in India but other geographies as well. And we had a Japanese member in our team, Dr. Tahei Fuji, was our Japanese partner. He is an ENT surgeon and in Japan. So he suggested that we use Inochi. So Inochi is a Japanese word which means life. So it resonated with all of us because it was easy to say, it was easy to write, it was easy for us to understand, and it resonated with the mission that we wanted to make the lives of the patients, the doctors and caretakers easier. So Inochi Care sounded like a name that we could relate with. Thank you very much.
Thank you, Mr. Siddiqui Pasi, for that wonderful session. Your talk has provided us with new insights and a deeper understanding of the subject. We sincerely appreciate your valuable contribution to this work.
Before we hesitate, we just want to say 2 things. One, anybody from third year over here, apart from these group? So he has introduced you the value of design fabrication project. So we were planning to conduct one session, and I request him to be present in that particular session, so that when your alumni tell you that what is the meaning of a particular course, probably you people understand more seriously. So maybe tomorrow or day after tomorrow, depending upon his convenience. The entire third year batch will organize one session. Second, I'm repeating again what I said yesterday also, that for us, all of us teachers, there are no more moments of proud than your students standing in front of you at this particular position. So that's another round of class for Nirmal and Ratan.
Can be joined with.
Ratan, you cannot give us, you can take also. If you feel them, please start. So we can't just tell you how, like मोदी जी कहते हैं ना 56 इंच का सीना 112
ऐसा
का
देख के हो जाता है।
112 का होता है।
इधर आ जाइएगा।
अरे वो टेंशन हो जाएगा, फिर सुधीर की एक और डिवाइस बनानी पड़ेगी।
And another second thing which I wanted to tell, and let's anybody from placement cell, otherwise I'll connect him to Umvir also,
Sponsors.
because he is offering you so many projects over there.
इसी कारण तो हम लोग होल्ड कर पाते हैं hope photographers are also taking order.
हाँ, ले लो।
Like telecast.
Shuffle box.
Thank you.
Now I would like to invite Professor Nishi Varsawa for presenting Memento as a token of appreciation as well as certificate to Mr. Sudhir Tripathi.
अभी सुनो।
You have to give.
हाँ, एक मिनट। पुनीत आप भी खड़े हो ना वहाँ पे। किसमें किसको?
So this process was also coming up.
इस साइड आ जाओ।
Get money from there.
ठीक आपको सर ने पढ़ाया होगा
हाँ yes
Girls may also come
नहीं
there.
he has been to University of Tokyo also उनकी लाइफ भी देखी है
You also have also.
उसमें ज़्यादा कुछ नहीं लिखा है हाँ ये चीज़
So we go for lunch after this.
चलो
Okay, and please carry your compass and green card. Also carry.